And it's working. Okay, cool.
Great.
So the way we typically do this also is that you can, people can ask questions just whenever, and you can answer them. If somebody asks a question on YouTube, I'll just ask you and you can answer it.
Okay, great. And so just go for the hour since people are asking questions in, okay. Mm-hmm.
Yeah, exactly. Some people, if you go over a little bit, it's not a big deal or anything, but.
I'm also happy to hang out afterwards if people want to, if they're available, I don't know, or we just cut it off an hour. Either way, doesn't matter.
Yeah, sounds good.
Okay.
All right, so welcome everybody. This is the second colloquium for the semester here at Augusta University in the School of Computer and Cyber Sciences. Today we have the pleasure to have Dr. William Bird, who's going to be talking about relational programming in miniKanren and how he applies this to using synthesis and treating rare diseases and things like this. Will is a scientist at the Hugh Call Precision Medicine Institute at the University of Alabama. He's also done a lot of really cool stuff in programming languages in general. So he's one of the co-authors of The Reason Schemer, which is a pretty popular book, and one of the creators of miniKanren, which is what he's going to be talking about it today, which I know I never pronounced the name right. So it's
miniKanren.
Kanren.
Okay. Kanren is Japanese for relation.
Oh, nice. Okay, I didn't know that.
It's not miniKanren. Everyone says miniKanren. It's miniKanren.
Yeah, I listened to your other talk, and I could have sworn people were saying it with an M. So I was like, okay.
They probably pronounce it every way you can imagine.
Yeah, exactly.
That's fine.
And so Will, go ahead, and I'll let you take it from here.
Okay. Hi. Yeah. Well, let's see here. I'm staring at myself. That's cool. Hi, I'm Will. I'm a scientist at the Hugh Call Precision Medicine Institute at the University of Alabama at Birmingham. There are 3 branches of University of Alabama. And actually, if you drive from Birmingham to Charleston, South Carolina, where I currently live, you will drive through Augusta, Georgia, where I assume Augusta University is located. Is that right? Okay. So
yeah, exactly.
I've never been to Augusta University. I'm giving a talk there, and afterwards, I still will have not been to Augusta University, but hopefully after the pandemic, we can remedy that somehow. So that'd be fun. So anyway, it's great to be here. Thank you for inviting me. And I'd like to talk to you about relational programming, which is a style of programming you may not have encountered before, or if you have encountered it, maybe you've encountered it in sort of a restricted manner. I'd like to talk to you about what happens if you try to generalize this approach to programming, which I think is very interesting. And, I've been working with many people now over the past 15, 17 years, something like that, to try to push this approach to programming and see what sort of secrets we can find. And, this is still an open story. I think there's a lot more to learn. I think we've only really scratched the surface of this style of programming. But if nothing else, I find it very interesting. It can be very frustrating. It's a frustrating, interesting style of programming where a 4 or 5 line program, you can spend years trying to figure out how to tweak it a little bit. So those are the sorts of problems I like thinking about. And I should mention that my original collaborators on this work and the people who got me inspired and showed me this approach to programming were Dan Friedman, who was my advisor at Indiana University, and Oleg Kiselyov. And so they were already working on a Kanren language, which actually Dan had been working on logic programming long before that. And there's a whole long story about the history of it, which is interesting to see. And I think that's been recorded on a talk Dan gave recently, sort of on the history of this, along with many other things. It was a Dan Q&A, asked Dan Friedman anything. So anyway, there's this approach to programming. I call it relational programming. I'm going to show you what it's about. Along the way, I'm going to show you a little bit of scheme, if you're not familiar with scheme, because in order to really understand what I'm going to show you, you have to understand some scheme. But fortunately, the parts of scheme that you need to know are very small, and I can cover that very quickly. And admit this miniKanren language I'm going to show you is also very small. So all of miniKanren, the core of miniKanren only is 3 operations, plus 1 interface operator between miniKanren and the host language. So I'm going to teach you sort of the cores of two tiny little programming languages, the core of Scheme, if you haven't already seen it, so that you'll know what a parenthesis is, you know what parentheses are, they won't scare you. And then I'll show you the core miniKanren, and then I'm going to show you some relations. Now, we only have an hour, and I don't have the time to show you in detail how to write all the relational programs. I'll show you a couple examples. I'll write at least one relational program, and then I'll talk to you about two other programs at least that we've written, and I'll show you how those programs work. But there's a lot more detail. And so if you're interested in finding more details, there's a website, miniKanren.org, that talks about the language and has links to papers and a book and my thesis and all sorts of other things. So you can find all sorts of resources at miniKanren.org. Okay, so without further ado, let me teach you a little bit of Scheme. Let me teach you just enough of miniKanren, and we'll start doing some relational things. One thing I will ask, if you've seen logic programming before, or constraint logic programming, if you've done a prologue, in the beginning, you're going to see some things that look familiar. I just ask you to be patient, because at some point, I think you'll see some things that you haven't seen before, but I need to kind of build up on some ideas. So, if you see some things you have already seen, trust me, there's new stuff coming afterwards, okay? Same if you already know Scheme, okay? Pretty sure you'll see something new. All right, let me share my screen. And I have one slide, because I want to talk to you at the end about some precision medicine uses of miniKanren. I have this disclaimer here basically saying I don't work for, I'm not speaking for the federal government. Okay, that's all. We have funding through the NIH NCATS Biomedical Data Translator program. And so that's for this miniKanren tool I'll show at the end. All right, that's my slide. So let's get into Emacs and let's learn some Scheme. Scheme, at least the part of Scheme we're going to use, is a very small language. And so we need to know about things like numbers. So 5 is a perfectly valid Scheme program. It is an expression that also evaluates to the value 5. So I can type in an expression and get its value. There are other types of values in Scheme. We have true values like #t and false values like #f. Sort of a technical side, every value in Scheme other than #f is considered true. Yeah, probably not so important for what we're doing. Okay, so we have true and false values, constants. We have, or literals. We have numbers like 5. We also have what are called symbols. So I can say, quote, cat, and that evaluates to the symbol cat. So this is a way to represent symbolic information. Like if I were representing a chessboard, I might have a piece which is a knight. Okay, this is different from a string. This is a symbolic value, this atomic. You can't really pull it apart. All right, so we have numbers, booleans, symbols. And beyond that, we have the ability to do things like add two numbers. So Scheme uses a prefix notation, parenthesized prefix notation. So here we're going to say that we want to add two numbers, 3 and 4. So the plus operator comes first. The parentheses in this case mean procedure application. We're applying the plus procedure, the procedure bound to plus, to 3 and 4, and we get back 7. All right. So similar to what you've seen before, it's just that we put the operator first, and I can do things like multiply 3 by 3 and square it, no problem. I can also construct anonymous functions, anonymous procedures using lambda. So I can say lambda x, have the body times xx. All right, so this is a lambda expression. Its value is a procedure that will take one argument. Let's call it x, and the result of applying that procedure to an argument will be to get back x multiplied by itself. So I can give a name to that procedure if I want. I can use define to give a name to a procedure. I can call a square. Okay, so now I have a name for this, and if I type in square, I will see that I have a procedure. bound to square. And I can apply that procedure with parentheses. And I can pass in 3, for example. And that will square 3. So I have 9. All right. And in addition, I also have the ability to do recursion with define, or I can use something called letrec, which is a recursive let, which I'll show you in a second. So I have the ability to define recursive procedures. And then there's one other thing that you need to know about, which are list structures. So I can build up lists. So there's one special list called the empty list. And then I can build up other lists using cons, which is a constructor. And so I can cons 3 onto cons 4 onto the empty list. And this will build a list of 2 elements, 3 and 4. And I can also, there's also a function called list, which can do the same thing, except it takes any number of arguments. It'll build up a list. And then one last thing I'll show you is that we have this quote operator, which I've already used twice, and that allows me to create quoted lists. So I can have quote 3, 4 that just evaluates the list 3, 4. All right, so that's a whirlwind introduction to the basics of scheme. One of the things that comes out of what I've already shown you is that if I have an expression like plus 3, 4, if I put a quote in front of it, now instead of evaluating plus 3, 4 as a procedure application, I get back a list, plus 3, 4, where plus is a symbol, 3 and 4 are numbers. This represents code. And if I want to, I can evaluate this quoted expression. I can evaluate that list. Notice the quote in the front. And then eval will treat the list I get back from the quote plus 3, 4 as if it were code and actually perform the addition. Okay, so I can go backwards and forth between expressions and values, lists representing code, for example, and then I can evaluate that quoted expression and interpret it. All right, so that's this idea of we can go back between code and data nicely. All right, and now let me show you this one last thing, which is we can also, with the lists, we can tear the lists apart. So I can take the car of a list that gives me the first element, and then I can take the cdr of the list, which gives me the rest of the list, or everything after the first element. And then I also can ask if a list is empty using null question mark, which will give me back false, unless the list is true. I mean, unless the list is the empty list, in which case I get back true. All right, that's plenty of scheme to do everything we're going to show you. And so now I'm going to just define.
Can I ask you a brief question?
Sure.
Is the question mark part of the name of the function, or is that an operator you add?
Good question. So we just type it in. Null question mark. Null question mark is bound. That's a variable bound to the procedure, which will tell you whether or not it's the list is empty. In fact, because scheme is flexible, we can do things like put this in a list. Okay, so I can say a list containing null question mark. All right, so now we have a list containing that procedure. And if I want to get that procedure, I can get the first element out of the list using car. And then, because parentheses mean procedure application, I can just wrap parentheses around that first expression and then feed in the empty list as an argument, for example, and I get back true.
Okay, thank you.
Okay. And of course, I could also build up a list that's not empty, cons 3 onto the empty list, and now I get false. All right, and I'll just show you one more thing since we're talking about quotes and expressions and so forth, is I already showed you that I can have functions like, well, let's do this. How about lambda x cons, x onto, cons 3 onto the empty list. Okay, so here's a function, and that will build up a little list based on the argument, and I can apply that procedure that I get back from lambda expression to, I don't know, how about 2? And now I get back to list 2, 3. Okay. And as we already know, if I put a quote in front of this expression, now I'm treating that expression as code, and I get back a list representing the code. All right. So that ability to go backwards and forwards, or in between, between expressions and treat the expressions as values, and from values treat as expressions. That's a really very important part of the scheme and Lisp philosophy. And we're going to be using this in a minute in relational programming. So I just want to give you sort of a whirlwind introduction. You can always, I guess, watch this video again on YouTube, slower speed, if this is a little too much. I know it's a lot at once, but you need to know this idea exists, okay?
There was a quick question on on YouTube.
All right.
They're asking, could you also say eval parenthesis plus 3-4?
Eval parenthesis plus 3-4 like that without the quote.
Right.
Yeah, yeah, absolutely. Absolutely. Okay, so this is important to understand. So what is going to happen here? What will the result be? Well, so what you have to understand is that actually there are two levels of eval. There's this little cursor here, this little prompt, this little caret. Okay, this is what we call the REPL, the read eval print loop. So we're evaluating this expression within scheme. And that read eval print loop itself has a copy of eval running. So there are actually two copies of eval. So this entire expression is being run within eval, within another copy of eval, another call to eval from the REPL. And so what's happening is that this expression is being evaluated. Well, eval is bound to a function. This expression is evaluated. Well, plus is evaluated to, or plus is a variable bound to a procedure that knows how to do addition. 3 is evaluates to 3, 4 evaluates to 4. So this sub-expression will evaluate to 7, and then we'll just evaluate 7. And in scheme, 7 evaluates to 7. So we'll get back 7, but not for the reason that you might think. So that's why we need to quote it. All right. If we're being honest, we want the evaluation to happen at the right level of eval. Okay. So there are sort of mysterious mechanisms happening. You really have to implement a scheme interpreter to understand everything, and I highly recommend that. That really tells you a lot about the heart of scheme. Okay, but that's a great question. That's exactly the right question to ask. All right. Okay, so hopefully you have enough handle now. Okay, so I'm running through this very quickly, but hopefully you'll have enough of a handle when I show you something in a little bit using eval in a different way. You'll be able to kind of understand what's going on, all right? Okay, otherwise you can get lost in sort of these details of how scheme works. I don't want that to happen. All right. Now, we know how to build lists using cons and the empty list. And we can take lists apart with car and coulter. We can test, see if a list is empty with the null question mark. And now one last thing I'll show you is I'll show you if we need some way to make choices. All right. So I can do something like if null the empty list, then return plus 3, 4, otherwise return times 3, 4. Okay. So this is an if expression. We have test. If the test is true, if the value of the overall if is the value of the sub-expression. Otherwise, it'll be the value of the sub-expression. So the null of the empty list is true. So therefore, we evaluate the first the first expression, and we'll get back 7. If I give this a list that isn't empty, like the list 4, then I get back 12. About the second one. Okay, so now we can make a choice. We have all the pieces we need. Now we can do something like define a recursive relation. Okay, now we can use define, but I'm going to show you another way. Well, okay, I'll just go ahead and do it define for now. I'm going to show you something equivalent to this, which is called letrec in a little bit. Okay, so this is going to be our hello world example that we're going to look at. This is append, list append. We're going to append 2 lists. All right. So this is all about, we're going to be dealing with recursion over lists. So if the first argument, which is a list, is the empty list, return the second argument. Else, we're going to cons up the first element of L onto the recursion. So we have a recursive call, the rest of L to S. All right, so there's a simple definition of append. Define allows us to do recursion, and now I can call append, and I can say, give me a list ABC and DE, append them together, and I get the list ABCDE. Okay, list append or concatenation, simple recursive definition using the pieces we've already seen. Okay, so that's hopefully enough of an intro to scheme that you'll be able to follow everything else. All right, that's the scheme language. Now, I'm going to load miniKanren, which also is a small language. And the miniKanren is actually much smaller than what I just showed you, far smaller. miniKanren is an embedded domain-specific language for relational programming. And so usually miniKanren is implemented inside of a host language. In this case, Scheme is the host language. So Scheme has an ability to add new syntax or redefine syntax, things like that. And so you can embed other languages inside of Scheme very easily. So we've embedded miniKanren inside of Scheme. And I'll show you the operators for miniKanren. So there's one really super important operator called equal equal. And it's a type of equality operator. Equal equal is either asking a question, you could think of it that way, or it is asserting that two things are the same, that they are syntactically equal. And so, for example, I could have list 3.4 and list 3.4. Okay, so we notice I have scheme expressions inside of equal equal. So we know list 3.4 will produce a list of two elements, containing 3 and 4, and so we'll list 3.4. And what equal equal is saying is that, hey, these things have to be the same. They have to be the same. Now, because this miniKanren is an embedded language, if I just hit return, I get back a procedure. Well, we've already seen procedures bound to things like null question mark. In order to actually treat this expression, equal equal expression, as or the value of it as a logic program or a relational program in miniKanren, we need to have an interface operator between the scheme language, the scheme host language, and the miniKanren embedded language. And that operation is called run. Run is our interface operation. So I can use run to create a query. The syntax of run is I have run, and then I have a number, which is saying how many answers I want to get back if they exist. Here I want one answer if it exists. And then I have a list of query variables. In this case, I have one query variable, but convention, we often use Q as a query variable. And then the body of the run is what we call a goal or goal expression technically. Okay, so we can run this equality operation, equal equal, which is based on an operation called unification. Technically, it's first order syntactic unification, if you know about unification. And so the question is, are these two lists the same? Is the question we're asking. Or more correctly, what I'm really asking is for which values of the query variable Q is it true that the list 3.4 is equal to list 3.4? Well, list 3.4 is always equal to list 3.4. It doesn't matter what the value of Q is. Q is irrelevant. It's not even involved in this expression, the computation of the equal equal expression. So it's true always for any value of Q. And that's what we see as the result. So we have a list of answers. And then in this case, we have a very abstract answer, _.0. What this is saying is our representation of Q, the query variable, is abstract. Q has not been given a concrete value. We have the abstract value _.0, meaning Q remains unassociated or fresh or whatever you want to call it. It doesn't have a value yet. Okay, so for all values of Q, it is true that the list 3.4 is equal to list 3.4 is one way to think about it. Now I can also violate this constraint. Instead of list 3.4 and list 3.4, I could say, what about the list 3.4 and list 3.5? When are they the same value? Well, never. They're never the same value. List 3.4 and list 3.5 are never the same value in Scheme, for example. And miniKanren, we treat it the same way. And so for which values of Q are the list 3.4 and list 3.5 the same? For no values of Q. And when we do the run expression, we get back the empty list. Okay, so there are no values of Q for which list 3.4 and list 3.5 are the same. All right, well, that might seem a little abstract, but it becomes more interesting when we involve Q in the equal equal expression. Okay, so I've slightly reformatted the code to make it easy to see how things line up. So here we're asking for which values of the query variable Q is it true that the list 3, 4 is equal to the list 3Q. And you can see that the 3's line up. Okay, well, that's fine. And then the 4 and the Q line up. All right. Well, in order for those two lists to be the same, Q has to have the value 4. And if I run the run expression, sure enough, I get back the list containing 4. It's not just 4, it's the list containing 4 because I can get multiple answers back, right? So this is saying there is a value of Q for which those two lists are the same. I can also put in, if I wanted to, multiple query variables. So I could say X and Y. So I could say, list X4 and the list 3Y are the same. So for which values of X and Y is it true that the list X4 is equal to the list 3Y? Well, in this case, we get back a list of values. So here we have the X value and here we have the Y value. So when X is 3 and Y is 4, then those two lists are the same, is how to interpret this answer. Okay, so that is equal. This is the big hammer of logic programming and relational programming, unification. So you've seen half of miniKanren already. We've got equal, and we've got run. Now, if you notice carefully, we've inherited part of scheme, part of our host language, because we have the ability to create lists, and we inherited numbers as well. So that's why I wanted to show you a little scheme in the beginning.
Hey, well, there's
yes.
Sorry, there's two questions for you.
Okay.
One was they say they didn't get the .0 part of the result. Should we interpret it as no occurrences in goal?
Okay, that's a good question. All right, well, I'll show you an instance where that's not the way to interpret it. Okay, so we could have something like this. How about here's an example for you. So now Q does appear in the equal expression. In fact, it appears in both arguments, the equal or both terms. So now we're asking, for which value of Q is it true that the list Q4 is equal to the list Q4? Well, for any value of Q. Q could be 5, Q could be another list. For any concrete value of Q you can come up with, those two lists will be the same. So you can think of this as sort of in logic when you have quantifiers. This is like saying that for any value of Q, these two things are the same. That would be one way you could think about it. Now, it turns out technically it can get a little more complicated. Okay, so I don't want to say it exactly means that, but that's a way to think about it. So we're saying, yeah, for any value of Q, it's the case that those two lists are the same. All right, so even if Q is involved in the terms or the arguments equal, you can still have the _0. Now, where it gets interesting, or it gets more interesting, we can also do this with, say, X and Y. And I can say, in this case, I have the list XY and the list XY. For which values of X and Y are those two lists the same? Okay. Now, in this case, I don't care what X is, and I don't care what Y is. It doesn't matter what their values are. And in fact, they could have the same value or different values, but this still works. This is still true. This still holds for any X and for any Y. And so when you see the answer, you'll see that X is _.0 and Y has _.1 as this value. So the .0 and the .1 are just to tell them apart. They don't really mean anything other than that. And so if I wanted to, I could actually get a little tricky here and I could swap the order. Now I'm saying the list XY and the list YX are the same. Well, that's fine. I didn't tell you what X is. I didn't tell you X is 5, for example. I didn't tell you what Y is, but I did tell you now that X and Y have to be the same value. And if I run this expression, then you'll see instead of _0 _1 like we got previously, now both X and Y have the same value. They're tied together. They're unified. If I ever give X a value, Y gets the same value, and vice versa. Okay, so that's what those numbers mean. And so let me go ahead and give you one more example. Now, it turns out there's a built-in conjunction or and inside of run. So I can do a second unification and I can say Y happens to be 5. And now when I run this expression, I have these two unifications. I get back X is 5 and Y is 5 simultaneously. They both have to be 5, even though I didn't say anything explicitly. I didn't explicitly say that X is 5. Okay. Now, one thing that's interesting is I can reorder those conjuncts. I can reorder the two equal equals, and I still get the same behavior. And within an equal equal, I can reorder the arguments to equal equal, and I still get the same answer. So this is a property of miniKanren in general, with a slight exception. Okay, there's a little cheat there. When reordering conjunctions, it turns out sometimes you can have infinite loops where other orderings might fail finitely, they might terminate, and vice versa. So there is a little caveat you have to be careful of, and that actually gets into the tricky parts of miniKanren programming. But that basic idea of being able to reorder things with both conjuncts and disjuncts, which I'll show you in a second, the disjuncts, we've tried very hard to try to preserve that. And Dan Friedman tried very hard with the reification of the answers with the _.0_.1 to preserve certain properties in the reified answers that you could depend on as well. So there's it took us a lot of time to try to figure out how to do this as well as we can. We're still actually working on how to improve it better with the conjunctions. Okay, so you've seen half of the language so far, and there's this implicit conjunction that I just showed you. And then there's one more thing that, okay, I'll show you one more thing with equal equal. And if, okay, so here's the question. So if I unify x with itself, okay, x is equal to x, for which values of x is that true? Well, probably by this point you could figure out that we're going to get back _0 for any value of x. For any x, we're going to x is equal to x. But there is a trickier problem, which is, what if I have x and the list containing x? For which values of x is it true that x is equal to the list containing x? Now here it gets a little more complicated. Turns out we could say that there is such an x that does exist. However, the x has to be infinite. Okay, we could allow what are called infinite rational terms. However, in miniKanren, we don't allow that. All of our terms are finite, and we are going to say there is no such x. All right, so we will get back the empty list. There is no such x for which this is true. This is implemented internally by using what's called the occurs check with unification. So if anyone knows Prolog, we always have the occurs check in miniKanren. Okay. All right, this is to make sure our unification is sound when restricted to first order syntactic terms. Okay, so that's enough about unification. Let me show you another part of the language. So another part of the language is cond. Syntactically, this is similar to a conditional operator in Lisp called cond, which I haven't, or yeah, I didn't show you this one yet. Okay, so here I can create different choices. This is sort of like an if. Okay, this is kind of like an if, or the possibility of a nested if. Here I'm saying either x is unified with 5 or x is unified with 7. So this is like an or a disjunction. Okay, I have two clauses, and they happen independently. Now, if I run this, what do I get back? Oh, well, x, my query variable, has the value 5. This is where you can see this number coming in, the run 1. So if I change the run 1 to a run 2, I say, all right, are there any other answers we could get? And I try it. Sure enough, I get a 5 and a 7. Okay, so the interesting thing here is, unlike if and scheme, or unlike cond and scheme, we actually try all of the cond clauses. Any one of the cond clauses can contribute an answer, is the way we say it. Okay, so we try everything, not just one. And these are independent. If you want to think of it from sort of an operating system standpoint, you could implement this. It's not implemented this way normally, but you could implement it this way, as saying each cond clause gets its own process or its own thread. And it, or process is probably more like it, because it doesn't share memory with anything else. You want to think of it that way. It's get its own copy of the memory, and it can't affect anything going on in another one of the cond clauses. These cond clauses are completely independent of each other. You can also think of it in terms of multiple worlds, that kind of thing. You can sort of make quantum analogies as well. You're sort of splitting off the world into two worlds. There's a world in which x is 5, and there's a world in which x is 7, and they don't know about each other. There's no interaction.
So,
But if we, yeah, go ahead.
another question was, I think you might have answered this earlier, but just to clarify, when you're thinking about these variables like x,
Mhm.
should we be thinking of them as existentially quantified variables?
Mm. Well, okay. So originally this was called exists, and in some sense you can think of them as existentially quantified. You can do a trick where you use a sort of a generated symbol that's lexically scoped, which is called a Skolem constant, and you can simulate quantification. But it can get tricky if you don't have the right mechanism, and standard miniKanren doesn't have this full mechanism. You know, if you use things like Skolem constants, you can start talking about universally quantified things, and you could talk about implication and so forth. That requires some additional mechanism that in particular has trouble when you have disequality constraints, like the negation story starts getting complicated. And so we've played around with it some, and we do have versions that have, you know, Skolem constants and so forth. And there are times I simulate them. In fact, I'll show you in a minute. Well, in a few minutes, I'm going to show you something where I simulate universal quantification using effectively a Skolem constant to get more quantification. But you can think of it really as like sort of an existential. If you get back an _.0 or _.1, you can kind of think of it as universally quantified, but to really do it right, you have to get the scoping correct. And that requires, like, you know, these like kind of lexically scoped generated symbols or Skolem constants. And you have to handle those properly so that you can do things like alternation of universal and existential quantification. If you want to do things like that, you have to build some more mechanism inside. And it becomes trickier. It becomes trickier to implement for sure. Cool. Especially when you have negation. Negation is the Achilles heel of full logic programming, let me tell you. Okay. That's why if people do things like answer set programming, there's like more restrictive.
Cool thing.
That's a good question. This is a great question. These are really good questions. Okay, so here we have the ability to get the two answers back. Now, once again, I can swap the Kandi clauses. Okay, swap the disjuncts, and I get back the same list in a different order. So in some sense, you can think of this as a set, or technically a multi-set of answers that happens to be represented as a list. Now, if I want to get all the answers for sure, I can do a run star. Run star guarantees I get everything. It doesn't matter how many clauses I have, because I can have more clauses if I want. You know, I could say 6. And the fact that I get 7 back before I get 6 doesn't really matter. You shouldn't think of it in terms of the ordering. Okay, think of it more like a set or multi-set. Okay, so we have Kandi, which allows us to do disjunction. We have equal, which is unification or equality, syntactic equality. And then we have run, and run has an implicit conjunction, and so does Kandi, by the way. So I can put in a y here as well, and I can say, you know, let me unify y as well in a separate unification, you know, unify y with cat. And now you can see that, you know, there's each Kandi clause itself has a conjunction. So Kandi is really a disjunction of conjunctions. Okay. All right, so you've seen 2/3 of the core language in miniKanren plus the interface operator. So I'll just show you the last operator. And the last operator for miniKanren, the last core operator, is called fresh, which allows me to introduce new, effectively existential variables. So I can do things like x, y, z. And once again, I have an implicit conjunction. So I could do something like inside the fresh, you know, I could unify x with, how about the list yz? And I could unify y with 5, and I could unify x with q, and now I get back this answer, which says, okay, you know, q is going to be associated with this list that has 2 elements, and the first element is 5, which happens to be the value of y, and the second element, it remains unassociated, and that's the value of z. Okay, so that's the entire core language. And I'll just show you one last thing that you will probably see. This isn't in sort of the minimal core language. You don't really need it, but it's very useful for expressing negation type things. There's also a disequality, which is sort of disunification. So you can say that Q is not 5. Whoops. Incorrect number of arguments. Oh. Equal/equal. All right. Let me make sure I didn't break sign. I'm going to try something real quick because I redefined append and I've learned the hard way. I think I redefined something used in miniKanren. So let's just try this real quick. Yeah, let's start Shea scheme instead of racket. That'll help. Okay, let's try it. Run star Q. Q5. Yeah, okay. So what happened there was when I redefined append was already defined. I redefined it as my example, and I clobbered the existing append. Oh, well. That's why namespaces and modules are useful and all that. Okay, so, and we do have versions that have that. I just didn't load that one. All right, so disequality is saying Q is not equal to 5, and the answer is saying, okay, Q can be anything. Here's how to read the answer. Q could have any value except we have this disequality constraint saying any value other than 5. And so if I ever violate that constraint, if I were ever to make Q equal to 5, then I would get back the empty list. This represents failure. We're talking about success and failure. Okay, and once again, it doesn't matter the order in which I put these two constraints. These are both constraints. Unification is a constraint, disequality is a constraint. And it doesn't matter what the order I write these in. Okay, so that's the miniKanren language. Okay, there are a few other constraints that we sometimes use, but that's basically the core language. Now, let me show you how we could define append, but in a relational way. All right, and yeah, so I'll just do this quickly. All right, so you can see that we have both define and lambda that we've inherited from scheme, but we also have cond to allow us to make a choice. We don't have null. So what I have to do is I say, okay, now I'll use equal, my unification operator. And actually in miniKanren, if we're going to find appendo as a relation instead of a standard function, I need to have what you might think of as an output argument or a third argument representing the concatenation of L and S. So basically the first clause, the first choice I have is if L is null or the empty list, then L plus S, which is sort of my output, or think of it as a result of concatenating L and S, that should be equal to the second list passed in. If the first list is empty, then the concatenation of the first of the two lists is the second list. That's what it's expressing. All right. Now in the second case, I'm going to introduce some local variables. All right, and I'm not going to explain this in any real detail. If you want to look at this, read one of our papers or my dissertation or the book or whatever, and you'll see kind of what's going on here. But the idea here is that I can do cars and cutters to tear apart L, but I can do it by unification of the pair of two logic variables or two of these miniKanren variables, unification variables. If I unify L with cons AD, this is sort of like a pattern matching. Unification is like a two-way pattern matching. So I'm saying L has to be a pair of the head and the tail, or the first and the rest. And if that's the case, then I'm going to call the head of that list A and the tail of the list, D. So sort of schemely names. And I'm going to call the recursive call for appendo on D and S, and I'll get a temporary result res. And now I'll say that L plus S is going to be cons of the first thing, A, onto res. All right. Now I've got a definition of appendo. Now what is that good for? Well, let me try running it. So I can do our previous example of appending ABC to DE. But now I have this third argument. We're going to put my query variable Q. So I'm saying you append ABC to DE, you get Q.
Yeah, right.
What did I do?
You should have the O, right? Appendo.
Oh, appendo. Yeah. Thank you. Yes. So now I run it, and now I get a list containing list A, B, C, D, E. All right. Okay. Well, that's fine. It's maybe not very interesting, but where it becomes more interesting is I can take the list A, B, C, D, E and say that's the third argument, and I can replace one of the first two arguments with Q as my query variable, and I can say, okay, what list, when you append A, B, C to the front of it, do you get A, B, C, D, E? And so it'll figure out that we have the list DE in that position. Or you could do it with multiple lists. So we could say we have the lists X and Y, and when we append X and Y, we want to get A, B, C, D, E. Okay, so saying if X is the empty list and Y is the list A, B, C, D, E, when appended together or concatenated together, you get A, B, C, D, E. And in fact, it turns out there's 6 of those examples. All right, so here are all the ways you can do it. And this is a standard Prolog example of append. This is like well known in Prolog. Now let me show you a problem. What happens if I ask for 7 answers? I told you there's 6 answers. If I ask for 7 answers, infinite loop. That's not so great. And this goes back to the problem with conjunction that I was talking about. Notice that I have this recursive call to appendo before this unification. Okay, so one of the rules of miniKanren is you always put the unifications or constraints before the recursions. And then if I reorder that, semantically, it means the same thing if an answer exists. But if there is no answer, it could be the difference between divergence and searching forever for an answer that doesn't exist versus termination. So now if I try, give me 7 answers, it terminates. I can do a run star now. I say, give me all the answers. And so now we can fail finitely and show that there are no more answers, right? So as a proof that there are no more answers. And so that's really gets to the heart of this sort of relational programming. Is the hard part isn't writing the program. The hard part is being able to prove that there are no more answers when you have potentially infinite many answers, infinite search space. Okay, and that's one thing that makes relational programming hard. Okay, so that's the append example. And you can find that in any Prolog book. Now the question is, what happens if you push that? What happens if you say, okay, append is great, but we want to do this for more complicated relations? What's a good relation? Or what's a good function that we want to turn into a relation? Oh, well, how about our friend eval that we saw in the beginning, right? Which eval is an interpreter. So what I'm going to do is I'm going to load a little interpreter. So let's load... is interp quote, I think I call it. All right, so I'm going to load a little interpreter. And so basically the eval, remember eval, so eval, I can give it, like a lambda expression, lambda xx, and it will eval that and give me a procedure. Well, now we have eval o, because we always put an O at the name of, at the end of our relation names. So we can do the same sort of thing. Now I need run for my interface, and I can say run 1q eval low, and I can say, hey, we want to evaluate the identity function and get back the value. Okay, so now we have a 2-place relation. I can call this val if you want to think of it that way. So here, I'm going to evaluate this expression to get this value. Okay, what's the value? Well, the value is a list that has this closure tag, if you know about closures. So this is a representation of a procedure, one way to represent a procedure. Okay, so the value of that lambda expression is a closure. But now we can start playing other games. Okay, so we can say, hey, now we know the value is the closure. Let me put the closure in the second position. And I'll say, I want to know which expression evaluates to that closure. Okay, so now we can run the interpreter backwards. Give me an expression that evaluates that closure. And if I run it, I get one in lambda xx. Hey, that was the original expression I typed in, but I can ask for more. I can say, give me a second expression that evaluates that closure. And now here's the second one. If I grab that and look at that expression, there's this little side effect there, or sorry, not a side effect, a side condition. So this is what the thing looks like. Now this _0 represents an arbitrary variable name. So I'll just pick one like y. So according to miniKanren, this relational interpreter eval, this expression gives you back something equivalent to the identity function. I can try it in Scheme. I could say, hey, okay, let me just apply that thing to 5. Sure enough, I get back 5. So this really is the, and I could pass in gensims and stuff. And, this is the identity procedure equivalent to it. So now I have the ability to start going forward and backwards. And so another thing is this interpreter handles, things like cons or list. So I can say, let's see, I want to interpret, for example, I want to interpret the expression, list, how about quote I, quote love, quote scheme. And sure enough, I get the list I love scheme back, but I can say, I want the value to be the list I love scheme, and I want to find an expression that evaluates the list I love scheme. And the first one is, okay, just quote the list I love scheme, but I could ask for 99 expressions. This is similar to a Matt Mike blog post where he's teaching lists to racket programmers, and I can get these sort of complicated expressions where if you actually run this expression, sure enough, you get back I love scheme. And so you got all sorts of lambdas and applications and quoted expressions. And once again, you have these very abstract answers, like whenever you see an _0 or an _1, and it has this symbol side condition that's saying that this could be any variable name, basically, is what it's saying. Okay, so now we can start doing things like that. Now it's time for a little quiz. So John McCarthy, who created Lisp, had this little paper. Here we go. Oh, no, the wrong one. Ah, here it is. Here it is. He wrote this paper.
There's a few questions on
okay.
YouTube.
Okay.
So one is, couldn't you also define an eval in Prolog that exhibited this behavior? I'm not sure what this behavior.
Okay, yeah, so this relational behavior, right? Could you write an interpreter as a relation in Prolog? The answer is yes. However, it turns out in order to do this well, you have to change many of the default settings of Prolog, and you also have to not use almost every operator in Prolog. So almost every operation in Prolog isn't actually relational. You have to get rid of cuts. You have to get rid of projection of numbers. You have to get rid of all sorts of other things. And if you notice, I said we have unification with the occurs check. We also have a special search, a special interleaving search that's complete that Prolog doesn't use by default. And it's neither depth first search nor breadth first search. So there are people who have done this in Prolog. Jason Heeman was helping people to do some of this in Prolog. It turned out to be much harder than you might anticipate in order to be able to do it well. In some sense, what you have to do is turn miniKanren, or sorry, turn Prolog into something like miniKanren, because think of it this way: miniKanren, in some sense, it has evolved over time to be a language optimized for writing relational interpreters and type inferencers and things like that. And so the constructs of the language, the search, and so forth. We've tried out various things, and now we have several constraints that make it easy to write interpreters in this style. And we've also figured out a bunch of heuristics we can use to speed things up and so forth. You can do these things in Prolog. Prolog makes a number of decisions that are different enough where you sort of have to undo them. So you have to start using occurs check, for example. You have to change the search fundamentally and not use one of the sort of baked in search. You can do that with Prolog meta interpreters. There are a bunch of other things that you have to do. You can do it, but it turns out to be harder than I think you would like. Okay, and I haven't seen people do this before in Prolog, other than copy sort of what's in miniKanren. Now I'm going to show you another couple of examples that go beyond this, and then I encourage you to try to do it in Prolog. If you can, let me know, because I think that'd be great. I think you'll find it maybe harder than you anticipate. For this example, maybe you could do it, but when I show you like the next two, then I think you'll find it harder. But okay. Great question. Yeah, absolutely. Mm-hmm. Another question.
Yeah, great. So there was one other one. Is using evaluate in some sense embedding higher order unification and first order unification?
Oh, these are great questions. These are great questions. Okay. That is a very, very interesting question. So for people who know about logic programming, there are higher order unifications, there's higher order pattern matching, and there are languages like Lambda Prolog that versions of Lambda Prolog either let you do second order unification or they let you do this restricted, sort of like second order pattern matching type thing. And it turns out that yes, when you start doing things like an interpreter for a Turing complete higher order language, higher order functional language like Scheme in miniKanren, in that first order language, you can start expressing things that feel like they're higher order. Now, of course, this isn't surprising in some sense, right? Like miniKanren is Turing complete, core Prolog is Turing complete. So it's not surprising that you can, you should be able to incorporate anything you can do by church, Turing thesis, anything that's computable and all that sort of thing, you should be able to, encode. But it turns out one way to do it, which is kind of nice and gives you nice properties, is by doing it through this relational interpreter. So that's one of the things we want to push. And another area I'd like to push is what happens when you have a miniKanren interpreter in miniKanren, and also what happens in the compiler story. And so there's a whole bunch of things we're trying to explore. And I'll show you in a minute with some of the other, okay, so this is sort of like the baby version of the interpreter. I'm going to show you a couple things in a minute that I think are more, go beyond what you've seen and bring up all these sorts of questions. But I think that's a great question. I would really like to understand more deep connections here. When you have, when you have an interpreter for, one of the things that happens is that negation becomes easier to encode in some way because we have not in the interpreter for Scheme. And so sometimes you can encode problems involving negation that would actually be tricky to encode in miniKanren. You can just encode it directly in Scheme. Now, there's obviously interpretive overhead and so forth. So I'm working with Nada Min and her student Laura on trying to do staged evaluation to get rid of some of the interpretive overhead. And there's a whole bunch of people working on the miniKanren, different projects to try to push it forward. But yeah, that's exactly right. I think there's interesting connections there I'd like to understand further. And I'll show you in a minute. I know we're running up on the hour, but let me show you a few things because now we're at like punchline time. Okay. So I'm going to show you like the stuff that's really cool. I'll do it quickly. I won't explain every detail, but hopefully I'll show you at least the things we can do. And then I'm happy to hang out for a bit. Okay. So we can do some things where we generate programs. Okay, so what I wanted to show you was John McCarthy had this paper, a micro manual for Lisp, where he sort of defines a Lisp in 2 pages. And the most interesting part to me is he says, difficult mathematical type exercise right here. Find a list E such that the value of E is equal to E. So E is some expression. E is an expression. And value is his eval. Okay, so he's saying we want to find an expression where the expression evaluates to itself when fed to the interpreter, when it's fed to eval. Okay, and this is what Doug Hofstadter has called a quine. Okay, it's a program that evaluates to itself. So we can take our evaluate and we can just basically type in what McCarthy expressed. We want to find an expression E such that the value of E is equal to the original expression. Okay? So just by putting in E twice, we can, through unification, say that the value and the expression have to be the same thing. And then when we run it, we get the canonical Lisp quine. Now there's some side conditions having to do with constraints just to make sure everything is sound. But here it is. This is the canonical quine, and I can just run it in Scheme, and we see we get back the same thing. And the interesting thing to me is there's nothing in our implementation of that interpreter that had anything to do with quines or program synthesis. We just wrote the interpreter as a relation, and we get this behavior sort of emerges from the relational paradigm. Okay, that's the sort of thing that I think people have trouble doing in Prolog. Okay, it's not to say you can't do it, and I would love to see Prolog tweaked, a Prolog that had the right settings to allow this sort of programming sort of out of the box and more easily. I think that would be really great and allow more people to explore this style of programming. But if you look at most Prolog books, they'll show append and maybe one or two others, but then they kind of stop and they start showing operations that are non-relational to control the search and things like that, or express negation. And you really have to stay entirely relational. You have to have a complete search. You have to have the occurs check. You have to have a bunch of things like that and really stick to the paradigm if you want to push it. Okay, so we can do things like Quine generation. Now, let me just show you one more interpreter, and we'll push it a little bit further, and we'll sort of tie it back to what we saw in the beginning with append. So let me do full interp. All right, so now we've got, I loaded a more sophisticated version of the interpreter that has a lot more of scheme implemented. This is sort of like the middle size interpreter that we have. And so once again, I can do the same things we were doing before with our evaluo. This is more sophisticated evaluo. So I can say like lambda x evaluates to q. And sure enough, now we have a more sophisticated closure that has a bigger initial environment. So same sort of idea though. All right, so here's what I'm going to do. And you know, Michael Ballantyne gets credit for this observation. So what Michael Ballantyne said is, well, okay, what if you defined append? You have the scheme interpreter. What if you defined append? In this case, I'll use letrec instead of define, but it's the same thing. What if you defined append, just the scheme version of append in miniKanren, in the relational interpreter? So this, I think, gets back to the question the person was asking about, does this give you higher order behavior? All right. And so here, we're going to write the version of append that I showed you earlier, except, you know, we're using letrec instead of a define, but it's the same thing. All right, and so we'll say append cutter eval to s. Okay, and then in the body of the letrec, we'll make a call to append. And so, you know, this is just a syntactically slightly different way of defining what I showed you before. All right, and I can run this. This is just the scheme definition of append. This is not appendo that we defined before. This is not defined as a relation. This is just the functional version. Notice that the lambda takes 2 arguments, not 3, okay? It's just a function. There's a clear input and output. And it's through evaluo, we're running this forward. We're just treating this as normal scheme code. Great. But because the interpreter is relation, we can say, well, we know the output is the list A, B, C, D, E. So we know the value. We can write down what the value should be. And then what we can do is we can go inside of the append and do things like put in the variable, the query variable, inside of the call to append. Say, okay, now I want to find a list that when you stick DE on the end gives you ABCDE. And sure enough, I get ABC. So now we can treat schemes, regular functional append, as a relation through the relational interpreter. But we can go further than this. We could ask ourselves, well, where else could we put a query variable? Well, what if we actually put it inside of the code for append? Okay, so here we have a car of L, and I'll put Q there and see what happens. Okay, guess what? We got back car of L. So now we're doing program synthesis through the relational interpreter. Okay, so we're actually able to put logic variables representing unknown values inside of the code. Now, I'm trying to show you one more thing, which is kind of the what happens when you push that further. All right, so if I can screen share one more time, I have to share it for this little window. Okay, so can you all see that? Yes. Okay, great. Okay, so this is Barlaman. This is a sort of a GUI that I slapped on top of this relational interpreter, a more sophisticated version I've worked on with Greg Rosenblatt, who added a bunch of optimizations, and Michael Ballantyne has also contributed to speeding up the miniKanren implementation, things like that. And so now, on the left, we have a skeleton of a scheme definition. So these comma A, comma B, comma C, those are logic variables. A, B, and C are logic variables. Those are like our query variables. We don't know what the A, B, and C are. Those are introduced with freshes. So we don't know the name of the definition. we don't know the arguments to the lambda, and we don't know the body of the lambda. So we don't really know anything other than we're defining some function. Now I can say, hey, let's define append through examples. Let's do example-based program synthesis. And I'll just put in the original call to append. In this case, I'll just put in the expression that we want to evaluate and the answer. Okay, so if I append the empty list to the empty list, I should get back the empty list. And now Bartleman thinks a little bit and comes up with proposed code. Okay, so it says, oh, you're defining a function called append. It figured out that A should be append, the symbol append, that's right. And it says, all right, well, in this case, it's really saying it's variadic because there's a side condition saying this is a symbol. The variadic function takes any number of arguments, and it's the constant function that always returns the empty list. Well, okay, that's true that it matches our example, but it's not very interesting. So let's give another example. So here I can say the list cat and the list dog. When I append those together, I should get the list cat dog. All right, and so let it think. And now it comes up with a more sophisticated definition that actually has a conditional in it. Now it's a little hard to read these variable names that are abstract, so I'll actually make this concrete. I'll go back to our old names, LNS, just to make it easier to read. And we can see, now we're starting to get some structure. We have an if, and we have a null test, and now we have cat dog are actually, those lists are appearing in the output. So there are one of two things I can do. I can either give some additional lists to say, well, you know, it should work in this case as well, in which case we can get more abstract answers. Or what I could do is I could get back to this question having to do about quantification. I can use what are effectively Skolem constants or lexically scoped variables. And I could say, you know, I want to have, so let's say I got G1 and G2, so those are my gensims, and I'm going to say I want G1 and G2, those lists to be the answer. And after it thinks for a minute, oh, I forgot my comma. Yep. Okay, so now it keeps it, the answer is going to be general. And I can add one more case here with G3, G4, G5, G6. And I can once again come up with the answer. So I'm going to say I want generic answers basically. So I want G1, G3, G4, G5, G6. All right. So when I have sort of arbitrary answers, I just care about the structure of things as opposed to the concrete values. It's sort of like a universal quantification type thing. Now I can get the full recursive definition of append. Okay. So anyway, that's Bartleman, and that's an interface on top of a more sophisticated version out of Allo that you saw. We have a Scheme Workshop paper from 2012 that talks about how to do the Quine version of the interpreter. And there's an ICFP paper from 2017 that shows how to do more of the Bartleman type synthesis, like append, and some more sophisticated examples. And if so, miniKanren.org has both of those papers. There's plenty more I could show you. I was trying to show enough background where people wouldn't get lost when I showed sort of the punchline. I didn't even get to talk about the precision medicine stuff. Let's just say that we're also using miniKanren to do things like graph databases and semantic web stuff as part of this translator project, using, trying to scale up miniKanren to be able to handle very large databases and do inference over that as well. So anyway, I know we're 9 minutes over, so if people have more questions, I'm happy to answer them. I'm happy to do more demos or whatever, based on what people want to do.
Yeah, cool. Great. Thank you so much. That was great. There were a couple questions, I think, that were left over. One person was asking about Prolog tabling and if that is useful.
These are great questions. Wow. Okay. I mean, yeah, most of the time I give this talk, I don't get these questions. There's like, yeah, like you're basically hitting our research agenda over the last 10 years.
Yeah.
Yeah. So tabling is super interesting. So tabling, if you're not familiar with tabling is like the logic programming or relational programming version of memoization. All right, where you want to save the results you've seen before. But what makes it harder in the logic programming setting or relational programming setting is that, first of all, you can produce infinitely many answers. Okay, so you can think of relational programming in general as sort of like having a relational database, except the tables can be infinite. They can have infinitely many rows. Well, it's the same thing with the memoization. You want to do dynamic programming, that's fine. You want to do memoization, that's fine. But when you can have infinite streams of answers, now it becomes much trickier to implement. And there's pretty complicated fixed point algorithms you have to implement to actually do tabling correctly. And there are also all sorts of questions. There are also versions of questions, like when do you consider two calls to a relation to be the same? There are the different notions of subsumption you can come up with. So all sorts of really interesting questions there. And also it turns out that once you've implemented tabling, you can then start doing things like co-inductive logic programming. You can start doing logic programming over streams. And there's been a lot of work out of UT Dallas. Gopal Gupta's group, for example, has done a lot with co-inductive logic programming. So lots of really interesting things having to do with tabling. We do have a version of tabling that was in my dissertation. Ramana Kumar and I worked on that for about a week. Well, over a summer, we were working with Dan Friedman, and we implemented that. It's really nasty code. It's probably the nastiest code I've ever written in my life. I mean, poor Ramana would implement it, and then we would debug it on the whiteboard for a day, or Dan's Blackboard for a day, and then we did this for like a week. And the code is like, you don't touch it. And this is the thing in logic programming. It's like, okay, you implement tabling once, and then you don't touch it unless you're XSB Prolog. There's an implementation in Prolog called XSB Prolog, where it's like sort of the main thing of that Prolog is its tabling. So it's super interesting, and it's also tied to things like abstract interpretation. Like there's really deep connections between tabling and abstract interpretation. And so what I want to be able to do is really push things much further with tabling. But it was as trickier than I thought it was initially. I think some of the more recent work we've been doing would make it easier. But another thing is, if you implement abstract interpretation algorithms and you implement you do things like tabling, tree automata, LVARs. If you've looked at that, like the Lindsay Cooper's work on LVARs and all that, you keep seeing over and over again that these fixed points over lattices, this code is like comes up everywhere, and it's really hard to get right, and it's hard to optimize, and a lot of times the code feels the same and looks the same. So one of the things I want to do now is create a language for doing fixed point over lattices computation, where that is like a fundamental, that is like the point of the language. Like view all computation as fixed point over lattices. What would that language look like? And could you do it so you could implement all those different systems in just a few lines of code and make it work well? I think that would be cool. But anyway, that's the other thing I think of. But yeah, tabling is super underutilized in some sense, so we haven't pushed that nearly as far as I want to. But yeah, there's lots of interesting problems with tabling. Tabling is super cool, and it goes far beyond just memoization in the functional world.
Yeah. Another question was, how do you control the search space in miniKanren so it doesn't explode?
Yeah, well, that's an interesting question. So, I guess part of the answer is not very well. There are times where you can tell you can get away with a depth first search, for example, right? And we could, do something like annotate those goals or those calls and say, okay, we know we can get away with depth first search. Although, in miniKanren, we've tried to keep away from like you having to have user annotations that could be wrong and lead to unsound behavior, that kind of thing. So I think a static analysis or dynamic analysis might help. In those cases where you can actually figure out that it's finite, for example. So the other thing is if you start playing around with the search a lot, you'll start noticing their connections with SMT solvers and SAT solvers. And there's things like conflict directed clause learning that those systems use. And so I think one approach would be to start building in more of those technology. We've played with it some, so not a min and Michael Ballantyne and a few other people have been working to do things like integrate Z3 into miniKanren, or Michael Valentine's done a lot where back jumping search and things like that. But it turns out there's this like impedance mismatch, because miniKanren search, which I haven't talked a whole lot about, Oleg Kiselyov came up with this clever approach to do a search where you're constantly interleaving between different streams. And so it's neither depth first nor breadth first, but it gives you some control where the conD clauses, the first conD clauses will get sort of more time initially than the later conD clauses. But there's this very interesting effect where if a stream is not productive and it doesn't produce an answer, that stream over time will start getting starved out, and the more productive streams will get more of the time. And so because of that, even if you write a miniKanren program, even if most of the conD clauses are divergent and they're never going to return an answer, and if one conD clause is returning answers, it'll actually work surprisingly well. And the other thing that seems to work well is that when you're writing an interpreter or whatever, normally you put your base cases first and your recursive cases later, and that matches up pretty well with the way that search works. So in general, we actually do much better than you might expect with these exponential problems. So we end up with this highly biased search. If you were to visualize it, here's some search tree is growing infinitely down like a triangle. Our search is like, like if breadth first search goes down like this and depth first search goes, our search is like this. It's like highly biased, sort of some direction, but it is complete. You'll eventually see everything. But certain areas of the search space are going to get a lot more time. That's sometimes what you want, sometimes not what you want. But it turns out for the sorts of program synthesis tasks, it works pretty well. But I do think that the next step would be, first of all, doing analyses to figure out when we can get away with more efficient searches. And then the other thing is integrating conflict-directed clause learning and things like that directly into the miniKanren search instead of calling out to an external tool. So see if we can figure out how to do that more efficiently. I think that would give us a lot of benefit. One of the things we figured out, we were advised in the beginning by a number of people to not even try this because Prolog's existed for 40 years or whatever, right? Yeah. And we were told you'd be 30 years back then, you'd be 30 years behind Prolog. And that's true, but Prolog's trying to do something different than what we were trying to do. And so, and what it turned out is, okay, you could have this super optimized, super engineered Prolog system, but it's optimized for something different. And often we could get away with kind of like a budget version of some constraint solving or something like that. But because it integrated with everything else well, like we actually got pretty good performance. And so that's my feeling, is that even if we have kind of, just a naive implementation of conflict-directed clause learning, and we don't have anything else, because it would integrate well with our interleaving stream-based search, we could get really good performance potentially compared to trying to integrate it to Z3 that has a different search strategy by default. So that's the hope.
That's cool. Thanks for sharing that.
Yeah. Got lots of research projects, by the way, if anyone's interested.
Yeah.
Got tons of research projects.
Any students out there?
Yeah, any students interested.
There's another question about what references would you recommend for someone wanting to look at the precision medicine applications of
Well, we've got a paper about to come out for the Scheme Workshop.
Oh, great.
And so that's probably the thing to start. If you find this interesting, I didn't even talk about that, but basically, I'll just give a nutshell summary of this precision medicine project. The idea is that there's both a problem and an opportunity. Over the past 40 plus years, there's been a tremendous amount of work in organizing information about biology, chemistry, medicine, drugs, chemicals, and so forth. And now there are all these ontologies that exist. There's semantic web technologies, all sorts of databases, and so forth. The problem is these are mostly siloed. So you'll have a really good collection of gene disease associations. And here you have a great database having to do with drugs and their properties and things like that. And now you have hundreds of databases, each of which is designed in a slightly different way. One might be a graph database, one's an RDF triple store, one's a, tab delimited text file, one is, a SQL database or whatever. And they have different schemas, they were never really designed to interoperate. And so part of the idea of this biomedical data translator project is to pull in and put into a standard data model, this BioLink data model, all these useful data sources, and try to massage them enough where they can, we can do queries over all the different types of data, do synonymization or normalization of concepts, and have a ontology for the predicates and things like that. So you can start asking sophisticated questions and start doing real reasoning. Now, one of the things I've been doing with Nada and Min at Harvard, and with Jeremy Zucker and Joseph Cottom at Pacific Northwest National Laboratory, which is really fun, is we've been playing around with old school symbolic AI systems, truth maintenance systems that came out of the Jerry Sussman's lab and John Doyle in the 70s and all these sorts of things. We've been implementing and use a combination of truth maintenance systems and Judea-Pearl style causal inference. And we've got this very good PhD student at PMI named Michael Patton, and he's currently working on integrating all the structured knowledge we have with electronic health records for patients, and also wet lab single cell RNA expression levels and things like that. And we're trying to integrate them together in a way where we can do causal inference and for things like COVID. And so this is really interesting, is trying to tie together very different types of information at different levels of granularity. But without this integration of all the structured knowledge, you're restricted to, only being able to ask kind of like these, keyhole type queries of one specific database, and then tying it, with a Perl script to another one or something like that.
Yeah, it'd be harder to explore, across all that data. You'd have to kind of like, oh, I know I'm going to fit in this one database, so I have to go there, as opposed to being like, oh, I have this general question, and then I can
That's right.
put it all together.
That's exactly the point of this project. And so there are many groups working part of this. And our reasoner is built from scratch. It's all built in Racket. It's built on top of miniKanren, or using miniKanren. And Greg Rosenblatt has implemented a graph database that talks to miniKanren. miniKanren is relational, and all the database stuff is effectively relational. Yeah. And miniKanren can deal with arbitrary arity relations, and so we can deal with triples just fine, and RDF type information and all that. And then he's been working on a new version of the engine, which also incorporates like data log type. Incorporates sort of like bottom up data log type evaluation, along with constraint solving, and it also involves the propagator mechanism, Alexei Radul and Jerry Sussman at MIT. Yeah, that's built into it as well. So anyway, we're using a lot of interesting computer science, I think, and PL techniques, trying to apply it to these precision medicine problems.
Yeah, that's awesome. That is really cool. There's another question here. It says SICK or CYC is supposed to support this kind of too, but you still have the problem of having to suck in all these different kinds of databases.
Yeah. So this is a Psych project. So Doug Lennett has been working on this for 20 plus years, 30 years. I'm not sure. They've been working for a long time, right?
Yeah.
And done a lot of very interesting work. And the Psych system has hundreds of millions, or I don't know, tens of millions at least, of different claims. I think his idea is that you need to be able to have understanding of the world in order to do real intelligent reasoning. So, as useful as these biomedical data sources are, they still don't actually know what a patient is, right? They don't know what a human is. And, they might know something about a chemical compound. They may know some information extracted from a paper, but they don't have any idea of what the world is about. And so doesn't know, a patient is a person who has gotten sick or something like that. Right. And so the idea of the Psych system is that, let's have all of these assertions and rules that we can reason over, and have many different types of logical inference, and have common sense knowledge about the world, and also be able to tie that to custom information. And that's a very powerful approach potentially. The reasoners and the data for the full version of Psych aren't available unless you just sort of do it commercially. So I think that's probably how kept it back some, and also I think it's pretty complicated. And so outside of that group, I think it's hard to know how to use those tools effectively. And so but I think a lot of that work is very interesting. Maybe that'd be a possible way forward as well. I also think there's a lot of low hanging fruit because, all this information has existed a long time, but no one's really tied it together very well.
Yeah.
There's also a DARPA project that's trying to do something similar. It's a big mechanism project from DARPA, which has somewhat shared goals. But you're starting to see now people very seriously try to tie together all these data sources and do reasoning over them together, which I think is the right thing to do. It's just, it requires a lot of, it's not something one group can do, right? It's not like you can write this one POPL paper, with three researchers or something. It's more like, okay, as a consortium, it's going to take years. You have to deal with data licensing, and you have to deal with, all sorts of standards and working groups, and it's a different type of beast than say writing a metacircular interpreter and scheme and playing with it.
Or like basic research, one research lab, single lab or whatever.
That's right. Yeah. So it's that's I think one reason why it hasn't been done as much as it could be is like you need to have buy-in, and people have expertise with lots of different communities, and it's definitely an example of extremely multidisciplinary work where we're working with biologists and physician scientists and computer scientists and experts in different areas of bioinformatics and computational chemists, and there are a couple hundred people involved in this.
Yeah, it's one exciting thing about it. I tell my students about this project all the time because it's such a great example of the multidisciplinary work and how computer science can be used to do more than just the typical thing that people think we do. So it's pretty exciting. I was wondering, does anybody on the Zoom have questions? I keep going to the. I figure people on Zoom will just like interrupt us and
people get mic shy.
Yeah, maybe. Yeah. Do you most of my work has to do with modal logics. Do you have any type of like this stuff might require some amount of modal reasoning, I suppose?
No. So we've implemented a few logics, but not nearly as many as I'd like to play with. So I would very much like to do modal logic and play around with that. Temporal logics would be also very interesting. Yeah. There have been some people, there's a miniKanren workshop now, and there have been people who've implemented temporal logic-based databases and miniKanren, things like that. And we've also done some work with nominal logic.
Okay.
Right. But there are many other logics I think would be interesting. I've never played around with modal logic and miniKanren. I think that would be interesting. There has been some work. There are enough people who have done projects with miniKanren now that I have to be a little careful when I say this, because there may be someone who's played around with modal logic, but I haven't played around with it. And what we have done things like there's this really neat solver for first order classical logic called lean tableau theorem prover, right? And the lean tab, like one of the best papers ever, the lean tab paper, the abstract for the lean tab paper is the theorem prover. That's the abstract.
Oh, right. Okay.
It's just a few lines of Prolog code, and then the paper explains the abstract. It's I thought it was brilliant. So we've done that in miniKanren using as a relation. We took this non-relational Prolog program and turned it into a relational by doing a special encoding in nominal logic. So Joe Neer did that when he was an undergraduate at Indiana. So we've done things like that, but for most things, for most logics, we haven't played around with it. There just now there's a higher order version. There's a lambda Kanren. There's a paper on that from Dan and his students at Indiana. That's in the latest version of the miniKanren workshop. So there are people starting to play around with these, but there's not nearly as much. I would like to also explore defeasible logic, linear logic, things like that. It's like default logics.
Someone was mentioning on the YouTube chat that does modal reasoning come into play with the staged miniKanren work? I guess it's a staged implementation.
Yeah, we're starting to do staged work. Actually, I'm skipping a call right now with Nada and Laura to do staged miniKanren. I don't know. That's a good question. It may. I don't know. One thing we just noticed was that it seemed like staging an interpreter and doing delayed goals in a logic system feel very similar. So there's like, you can implement delayed goal mechanism where you say, okay, I want to run this goal, but I don't have enough information. Like the arguments to the goal or the relation are not ground enough yet. And so like, say you want to do sine and cosine for, maybe you want to do probabilistic logic programming and you have to do things like sine or cosine or whatever, or log values, over floating point numbers or something like that. You probably don't want to write some sort of heroic solver that's purely relational. You probably want to wait until the arguments are ground enough, just delay those goals until the arguments are ground enough where you can just call schemes version of log or whatever. And when you implement that feels very, very similar to doing staged version of the miniKanren interpreter. And so that's one of the things we're looking at. It's like, what are the connections between staging and delayed goals? Because it feels so similar. It's the same thing of when you do the tabling, right? Like tabling feels so similar to other types of things that I've implemented. I'm sure there are really deep connections there.
Yeah, sure.
Yeah.
That's cool. All right. Yeah. Does anybody else have any other questions before we head out? This one it's 2:30, so.
That was really cool. Thank you.
Oh, thank you. Thank you for coming. I didn't even show you the theorem prover running backwards. You can write type inferencers this way. You can write theorem provers, right? That was actually one of the punchlines for the ICFP paper. Matt Might had a theorem, had a proof checker. It wasn't even a theorem prover. It was just a proof checker. So he had a proof checker written in Racket, and we literally just took the proof checker and ran it in the relational interpreter, and it turned it into like a really crude proof assistant or theorem prover.
Oh, yeah, cool.
Automatically do the search for you, right? And that was great because like it was never designed to be anything other than a proof checker. You had to give it the proof and the theorem, and it would just give you true or false. And,
yeah, sure.
Yeah, so that stuff's really fun. Now making it perform well, that's not so easy.
Sure, yeah. Then you got to.
Yeah, that's right.
All right, cool. Well, thanks a lot, Will. This was really great.
Yeah, thank you. If anyone's interested in talking more or doing some research or doing a project or anything like that, just let me know.
Yeah, great. Awesome. And thanks, everybody. Appreciate it, especially all the questions from YouTube. That was great.
Yeah, thank you.
That's it.
Okay. Bye-bye.
See you later, Will.
Bye, Mitch.
Great.